In the AI era, spinning up a dozen app servers is trivial. You write a prompt, set an autoscaler, and walk away. But there's one layer where every system eventually crawls to a halt: the database. Servers are stateless, so you just clone them. But the database is stateful. It holds the data, the disk, the writes. If it bottlenecks, the whole system collapses. Last time, we scaled the servers and the load balancer. Today, we conquer the storage tier from the ground up. Picture the very start of a design. Your app is growing, and you have to make a real call. Do we store this in a relational SQL database or a non-relational NoSQL one? Answer that based on whatever's trending this week, and you'll fail the interview. You choose on your data and your access patterns. SQL means strict, predefined tables, rigid rows and columns with relationships enforced by foreign keys. And here's the real power. Want a user's full order history? SQL stitches the tables together on the fly with a join. Just follow the keys from one table to the next. Its superpower is ACID. Watch a bank transfer. Money leaves account A, heading to B. The transfer fails halfway, and the database rolls the entire thing back cleanly. No money vanishes into thin air. That all-or-nothing guarantee is exactly why banks, payments, and orders almost always live on SQL. But that power has a price. Joins and ACID stay cheap only when all the data sits on one machine. To stay consistent, the database leans on locks. Try to split your tables across two machines, and every join has to cross the network while every transaction waits on a distributed lock. It crawls. So instead, SQL scales vertically. You just buy a bigger box. And like part 1 showed, vertical scaling hits a hard ceiling. NoSQL drops the strict tables. Data lives as self-contained JSON documents, key value pairs, wide columns, or graphs. And because each document already holds everything it needs, reading it is just one lookup on one machine. No join, no stitching tables together. Because each document is self-contained, with no joins holding it back, copies scatter effortlessly across hundreds of cheap machines. Horizontal scale, baked in. But that freedom has its own price. To stay fast, the very same data gets copied across many nodes. But you give something up. NoSQL leans on eventual consistency. Update your profile picture, and it takes a moment to reach every node on the planet. So when do you pick which? If you need rock-solid transactions, complex relationships, and joins, think payments, orders, banking, inventory, you reach for SQL. But if you need massive scale, a flexible schema, and fast, simple lookups, think feeds, chat, sessions, or sensors. Okay, say we picked SQL. We launch, traffic hits, and the database starts choking. Now what? First, read the traffic. On most apps, Twitter, a store, it's lopsided. People read about 90% of the time, and only write maybe 10. Now, it's tempting to immediately shard across 10 machines, but that's the nuclear option. Way too complex for this. Instead, replication. You pick your main node as the leader and spin up exact copies called followers. Every write, insert, update, delete goes only to the leader. The leader applies it, then streams the change down a replication log to every follower. And every read skips the leader completely and spreads across the followers. Just like that, 90% of your traffic is off the primary. But the network isn't instant. It takes time for a write to reach every follower. That gap is called replication lag. Picture it. A user updates their profile picture. The write lands on the leader perfectly. They refresh immediately, but their read hits follower 3, which hasn't gotten the update yet. They see the old picture. They assume it's broken and slam the button 10 more times. The production fix is read your own writes. Right after someone writes, you route their reads to the leader for a few seconds. So they always see their own change while the followers quietly catch up. Great, reads are balanced, but replication copies the whole table to every machine. What happens when that one table itself gets monstrous? Even with replicas, every copy still holds one giant table. Run an app for 5 years and a single orders table balloons to hundreds of gigabytes. Now every query forces the engine to scan a massive, bloated index on disk, and your queries crawl. And again, do we leap to sharding across 10 servers? No, that drags in huge network overhead. First, we try something local. Partitioning. You break the table into smaller, independent subtables, split by a boundary like time, 2024, 2025, 2026. To your code, it still looks like one table. You run a normal query. But ask for an invoice from March 2026, and the engine uses partition pruning. It ignores 2024 and 2025 entirely and dives straight into the tiny, fast 2026 slab. But notice, every one of those partitions still lives on the same single machine. If your data outgrows that one disk, or the writes pin that one CPU at 100%, partitioning can't save you, and that's when we finally pull the nuclear option. Sharding. The hand finally slams the stamp down. Earned at last. Sharding breaks one massive table into chunks called shards spread across completely separate machines. 100 million users no longer sit in one table. Machine 1 holds the first 33 million, Machine 2 the next, Machine 3 the rest. Separate disks, separate CPUs, now you've scaled writes horizontally, infinitely. To find a user's data, the app uses a shard key, say user ID, and a routing algorithm to pick the machine. And the algorithm? It's the consistent hashing we mastered in part 1. Same ring, now deciding which database holds your row. But sharding has 3 traps interviewers love. 1, cross-shard joins. The moment a query needs data from 2 shards, the engine hauls rows across the network and stitches them in memory. Brutal and slow. Trap 2, hotspots. Pick a bad key, like sharding a store by product category. When electronics goes viral on Black Friday, that one shard hits 100% and dies, while the others sit idle. Now you have to re-shard, redistribute everything live. Operationally, a nightmare. And trap 3, the celebrity problem. Put a user with 80 million followers on one shard, and every single post slams that one shard with a spike no normal shard ever sees. So that's the whole toolbox. Now let's put it to work on a real system, Uber. Classic interview prompt. Design the data layer for Uber. You've got 2 totally different beasts. 1, billing and payments has to be exact, auditable, never wrong. The other, live driver GPS, is millions of coordinates a second, where a location is worthless a minute later. Billing screams SQL. If a card is charged but the payout fails, the whole thing must roll back. Pure acid.
So a powerful PostgreSQL leader takes every right to guarantee integrity and read replicas serve receipts and history.
And as years of ledgers pile up, we partition by time, not shard randomly. So old data stays cold and new transactions stay fast. GPS is the opposite. Write-heavy, ultra-high throughput, and consistency barely matters. Eventual is fine. So we use Cassandra, a wide column ring with no single master. It auto-distributes rows on a consistent hashing ring, exactly like part 1. The trick is a composite key. The partition key, driver ID, hashes each driver evenly across the cluster, so writes spread perfectly, no hotspots. And the clustering key, timestamp, keeps each driver's points pre-sorted on disk by time.
So where's my driver right now is a sub-millisecond point lookup. The data's already sorted.
Same engineer, same toolbox, 2 workloads, 2 completely different correct answers. Underneath all of this sits one law interviewers love, the CAP theorem: consistency, availability, partition tolerance. In a distributed system, a network partition will eventually happen. And when it does, you're forced to pick: stay consistent or stay available. You can't have both. It maps perfectly onto Uber. Your billing database is CP. If a replica falls out of sync, it would rather refuse to serve than show a wrong balance. Your GPS database is AP. If a node drops, the others keep taking coordinates and reconcile later, so the writer's map never errors. So the toolbox. SQL gives you consistency in joins, but scales up, not out. NoSQL scales out forever, but trades instant consistency. Replication fixes read-heavy load, but adds lag. Partitioning speeds a giant table on one machine, and sharding splits across machines for infinite scale at the cost of real complexity. But there's still a hole. If millions of writers keep refreshing drivers near me, every refresh hits our databases directly, pounding the disks for data that barely changed. We need a shield in front of the database, and that's the next piece of the roadmap: caching. Which database setup are you running? Tell me in the comments. Like, subscribe for part 3 on caching, and I'll see you in the next one.